Welcome to Math with Professor V. In this video, we're going to learn how to find the radius and interval of convergence for a power series. I'm going to work through 6 examples, and by the end, you're going to be a professional. It's going to be fabulous. Now, if you haven't watched the introductory video lecture on power series, what a radius of convergence and interval of convergence is, I'm going to link it here. Just click in that top right. But the purpose of this video is just to work through a lot of examples. That way you can be a professional by the end and not be afraid of this kind of problem. But just as a recap, a power series has the following form. It's the sum, n equals 0 to infinity. I mean, you can start at 1 too, okay? Of c sub n times x minus a to the n. So what you want to think of it is like this c sub n, that used to be our an. When we had a regular series, not a power series, right? Usually we would write it out. It was the sum, n equals, we could say 0 or 1 to infinity of a sub n. That was a series. Now we're calling this c sub n when we're talking about a power series because those are just like the coefficients. And then now we're throwing in an x, minus a raised to the n. So what happens, each of the terms has x minus a in increasing powers, okay? On and on forever. So this is equal to some function f of x as long as this series converges. And there's 3 possibilities. Either your radius of convergence is some constant, and then you have an interval of convergence. Your radius of convergence is a constant, but it's 0. So then your interval of convergence is only where the series is centered. We'll do one like that, don't worry. And then the last case, my favorite, is when the radius of convergence is infinite and x can be any real number. You don't know when you're first looking at them usually. You're going to have to actually go through a test to determine which of the 3 cases you have. Okay, so I'm just going to jump right in. I don't want to make too talky of a video. Let's just work on solving some examples. Find the radius and interval of convergence for each power series. So I will tell you 99% of the time, the best thing to do is use the ratio test. There are a few instances where the root test is better, but if you don't notice and you do the ratio test, you'll be just fine, okay? But if there's time at the end, maybe I'll throw in lucky example number 7 and we'll do a root test just for you to see, okay? Fab. So here we go. Find the radius and interval of convergence for each power series. I'm going to go ahead and do the ratio test. Tell the people what you're doing. It's always good. Oh, we're doing the ratio test. So I'm going to take the limit as n goes to infinity, absolute value, an plus 1 over an. I'm assuming you remember the ratio test. If you don't, in the description, I have all of the video lectures linked in Calc 2, especially this unit, so you can go through refresh should you need. Okay, here we go. So I'm going to have the limit, n goes to infinity, absolute value. I'm going to substitute in n plus 1 everywhere there's n. So we'll have x to the n plus 1 over, now be careful, be so careful, 2, please put parentheses around the n plus 1. I have so many students, they mess that up. So don't forget you need parentheses there, okay? Divided by an, so this is all divided by the original x to the n over 2n minus 1. How we doing? Good? Okay, clean up time. Limit, n goes to infinity, absolute value. X to the n plus 1, I know I'm going to have some sort of cancellation situation coming up. So I'm going to break it up into x to the n times x to the first. Okay, so this is right here. And then this denominator, let's clean it up. So this is 2n plus 2 minus 1. 2n plus 2 minus 1. And then I'm dividing by all of this, so I'm just going to multiply by the reciprocal. So I'll have now 2n minus 1 in the numerator and x to the n in the denominator. So far, so good? Beautiful. So look, we can have ourselves a little cancel party here. X to the n cancels out. And that's it. Okay, don't get too excited with this cancel party. So let's rewrite what we have so far. We have now the limit as n goes to infinity, absolute value, x over, now this is just going to give me 2n plus 1 times, I have 2n minus 1 over 1. Okay, from here, you're going to do pretty much the same process with every problem. I'm taking the limit as n approaches infinity. So in this limit, x is a constant. X isn't changing. N is changing. X is a variable, right? But in the limit, it's not changing. So I can take this outside of the limit, okay? But I do need to remember to put the absolute value bars around x when I take it out, because x could be any real number. So I need to preserve the absolute value. So I'm going to rewrite this as absolute value of x, limit, n goes to infinity, and then now I have 2n minus 1 over 2n plus 1. And you know what? I don't have to keep putting absolute value because n isn't going to be negative and it's going to positive infinity. So if you just want to switch to parentheses when you have only n's, please feel free, please. Okay, from here to evaluate the limit, I'm looking, the numerator goes to infinity as n goes to infinity, and so does the denominator. Infinity over infinity. So what do? I hope you did not say use L'Hopital's rule. No, no, no. You can only use L'Hopital's rule on functions that are differentiable. This is not a function, okay? So instead, what I'm going to do is divide by the highest power of n from the denominator, which is n to the first. That was how you first learned how to do these limits before you learned L'Hopital's rule. So just go back in time. Pretend you didn't even know L'Hopital's rule, okay? And then let's see what we have here. So this is going to give me absolute value of x times the limit as n goes to infinity. If I distribute this through, it'll be 2 minus 1 over n over 2 plus 1 over n. Oops, beautiful. And then as n goes to infinity, each of these little 1 over n's goes to 0. So then I'm just left with 2 over 2, which goes to 1. So at long last, my limit is absolute value of x. That's it. Okay, well, think to yourself, which test did I just apply? Do you remember? Yes, we used the ratio test. And what do we know about the ratio test? Well, in order for a series to converge, whatever the limit comes out to be from applying the ratio test needs to be strictly less than 1. So we impose that condition to ensure the convergence of our power series. All right? As long as on the left-hand side of this inequality, there's no coefficients on x, okay, then what's over here is your radius of convergence. So I can say my radius of convergence is equal to 1. That part's done. We'll look at examples where it's not 1. Don't you worry, okay? Now, to find the full interval of convergence, I'm going to have to test the endpoints. So my next step is I'm going to rewrite this inequality without the absolute value. If you have absolute value of x is less than 1, that's the same as saying x is less than 1 and greater than negative 1. So my two endpoints are negative 1 and 1. And I need to see whether either of these inequalities is going to become inclusive or not. So what do? I'm going to have to do 2 separate tests and plug in each of these endpoint values to the OG power series. Are you ready? Oh, good. Let me copy it. So many of my students have tablets and iPads. And I told them, I wish there was a way we could take the test on it, you know, so you could do these copy-paste maneuvers. So now we're going to test our endpoints. The first one I'm going to test is x equals negative 1. Okay, so x equals negative 1. So you're literally just going to substitute in x equals negative 1 right here. So let's write out what our new series is going to be. We have the sum, n equals 1 to infinity, negative 1 to the n over 2n minus 1. Okay, well, this is an alternating series. How do I know that? Because I see this -1 to the n. That's my big clue. So let's go ahead, let's use AST to determine whether or not this converges or diverges. So B sub n, you just ditch the alternating part. It's 1 over 2n minus 1, and there's two conditions I need to check. Is Bn decreasing? Well, I can just go ahead and use the direct definition. B sub n plus 1, that would be 1 over 2 times n plus 1 minus 1. And that's for sure less than 1 over 2n minus 1. How do I know that? I just made the denominator bigger. So obviously this entire expression is smaller. That term is smaller. And this is Bn. So that's our definition of decreasing. If you can show that Bn plus 1 is less than Bn, that is satisfied. Done. Second condition, do you remember? Yes, we look at the limit as n goes to infinity of Bn. And in this case, I have a constant over infinity. Anytime you have a constant and the denominator, constant in the top and the denominator is getting very, very big, this thing's going to 0. And that's the second condition I needed to satisfy. So that tells me that the sum, n equals 1 to infinity of -1 to the n over 2n minus 1 converges by the alternating series test, which also tells me that x equals -1 belongs to the interval of convergence. So the way you write that is it's an element of, or it belongs to, the interval of convergence. So now I know I can make this an equals to, okay? Well, I have one more endpoint to test, +1. So let's hop to it. Here we go. So x equals +1. What's that going to make our series? So we're going to have the sum, n equals 1 to infinity, 1 over 2n minus 1. Okay, you have a few choices on what to do. I had a few students do the integral test. How lovely. I think it's a little more work. I wouldn't choose it. I'm looking at this guy and I'm like, okay, it reminds me of harmonic. It's giving me harmonic vibes, harmonic series. But I've got this -1 in the denominator. So that means this is a little bit bigger than the harmonic, but then this 2 kind of makes the terms a little bit smaller. So I can't use direct comparison. It won't be clean, but I could do limit comparison test. So let's go ahead and set that up. So I'll just say, remember our friend, the harmonic series, n equals 1 to infinity, 1 over n. You have to tell the people you know who that is and what it does. It's harmonic, it diverges. I'm going to use the limit comparison test and take the limit as n goes to infinity of the terms of my series divided by the terms of the harmonic series. So this is going to become the limit as n goes to infinity of n over 2n minus 1, yes? And then again, we're in a situation that we just saw a few minutes ago. Top is going to infinity, bottom's going to infinity. No, we're not doing L'Hopital's rule. No, no, no. We're going to divide top and bottom by n. You could write times 1 over n or divided by n. It is the same thing. Do what you like better. So then this is going to be the limit, n goes to infinity of 1 over 2 minus 1 over n. So this goes to 0, and my limit ends up being 1/2. Well, when you do limit comparison test, what is important about the result of the limit? Two things. It needs to be finite, and it needs to not equal 0. If you get infinity or 0, what that means is most likely you compared it to the wrong series. Okay, so if the test will give you no information because it wasn't set up properly. So try again. Pick a different series to compare it to. Change this guy up if you get infinity or 0. If you get some other non-zero constant, then what the limit comparison test tells you is that our series does the same thing as the one we compared it to. So I compared it to the divergent harmonic series. So what does that tell me? That means my series also diverges. They're twinsies. Also diverges by limit comparison test. So that further tells me that x equals 1 is not in the interval of convergence. No, no, no. So -1 is, but +1 is not. So if we want to write out our interval of convergence, put a bracket on -1 and parentheses on +1. It's not included. Okay. Good. How are we doing so far? I went through that one very slowly. I'm going to kind of pick up the pace on some of the details and the algebra in the further examples, okay, just so we can see some more. So example 2, we have the sum n equals 1 to infinity of x to the n over n to the 4th times 4 to the n. Again, ratio test will work just fabulously for this, so let's go ahead and use it. I thought I had a black one. There we go. Okay, let's use the ratio test. And here we go. We're going to take the limit as n goes to infinity of the absolute value, an plus 1 over an. I'm already going to just hop to it. X to the n plus 1 over n plus 1 to the 4th times 4 to the n plus 1. And then I know I divide by an, but will you all be okay if I already multiply by the reciprocal? Is that going to be fine? Oh, good. So then this is n to the 4th, 4 to the n over x to the n. Okay, so now let's start breaking things up so we can have ourselves a little cancel party in a moment. So limit n goes to infinity. I'm going to rewrite this numerator as x to the n times x to the 1st. This is n plus 1 to the 4th, 4 to the n times 4 to the 1st. And then here's n to the 4th, 4 to the n over x to the n. Good. Let the cancel party commence. X to the n goes bye-bye. Who else? 4 to the n. Very good. Very good. And I think that's about it, right? Okay, very nice. So here, let me rewrite it. We've got the limit as n goes to infinity. And let me take out anything that doesn't involve n, okay? So I can take out this 4 and x out of the limit. They're not n's, so they're constants in the limit. So I'm going to rewrite this as absolute value x over 4 times the limit as n goes to infinity. And then now this is just going to be n to the 4th over n plus 1 to the 4th. Okay. So now to take this limit, again, you have infinity over infinity. I want to divide by the highest power of n from the denominator. And let me show you kind of like a slick way to do it, because I mean, I personally don't feel like foiling this all out. Do you? No, we certainly don't. And we don't need to. That's the best part. So I'm going to rewrite this as absolute value x over 4 times the limit as n goes to infinity. Now you're going to group these guys together. N over, n plus 1 to the 4th. And now I'm going to divide by n to the 4th. Divide by n to the 4th. And when I put it inside those parentheses, it's just going to become plain old n because it's already going to get raised to the 4th in the parentheses. Okay, so then we have absolute value x over 4 times the limit as n goes to infinity. And this is going to be now 1 over 1 plus 1 over n to the 4th. Did you catch that? That was a very slick move. But believe me, you want to learn how to do it. Okay? Good. So now as n goes to infinity, 1 over n goes to 0. This limit's just going to be 1 over 1 to the 4th. So this all goes to 1. And I'm just left with absolute value of x over 4. That's my limit. Nice. Now remember, we did ratio test. So in order for this series to converge, this limit must be less than 1. We impose that condition. From here, I have to clean up a little bit before I can determine my radius of convergence, because there's a coefficient on x, or x is being multiplied by a constant. divided by 4 is the same as multiplied by 1/4, right? So let's get x all by itself. This means absolute value of x is less than 4. Exactly. You just multiply by 4 on both sides. It's okay that it's in the absolute value. We just make it a positive constant and you're good. So absolute value of x is less than 4. So that's my radius of convergence. R is 4. Okay. Now, let's see, we have to test our endpoints. So if you'll remember, when you have absolute value of x is less than 4, that means x is less than 4 and greater than -4. So we need to test our endpoints. Let's tell the people that's what we're doing. Test our endpoints. Let's do -4 first. So x equals -4. Where do I plug it in? Into the original series. Where did you go? Right here. Copy, come down with me. Okay, so we're going to have now the sum, n equals 1 to infinity, -4 to the n over n to the 4th times 4 to the n. Okay, let's see here. Now, both -4 and 4 are being raised to the n. So I can rewrite this actually as the sum, n equals 1 to infinity, -4 over 4, put them together to the n, times 1 over n to the 4th. And then look, this is just going to give me -1 to the n. So I can rewrite this as the sum, n equals 1 to infinity, -1 to the n over n to the 4th. Okay, what do you want to do from here? You have a couple choices. You could do AST because it's an alternating series, but I'm going to show you a little bit of a different approach that I think is a little faster. Even if this was not alternating, so if we didn't have this term up here, this series would still converge because n to the 4th is a piece series. So I'm just going to say that. I'm going to actually show that this series is absolutely convergent, and absolute convergence is the strongest kind of convergence there is. So that implies that it's convergent. If you struggle with that concept, you are not alone, and I have a lovely little video and an excellent analogy to help you understand. Let me link it right here on absolute and conditional convergence. It'll help you. But that's what I'm going to do. So I'm going to say, hey, these terms here, that's an, and the absolute value of an is 1 over n to the 4th. And I know that the sum, n equals 1 to infinity, of 1 over n to the 4th is a piece series. P is 4, which is greater than 1, so it converges. That tells me x equals -4 is in the interval of convergence. It belongs to the interval of convergence. Done. You didn't have to do condition 1, condition 2 for AST. I think this is faster. If you hated this approach, then just do the AST, okay? And then we have the other endpoint, +4 to test. And again, this one's going to be pretty straightforward. We have the sum, n equals 1 to infinity, 4 to the n over n to the 4th times 4 to the n. This one's even better. Look, these cancel. And then all I'm left with is the sum, n equals 1 to infinity of 1 over n to the 4th. Well, I just said up above, it's a piece series and converges. I don't need to rewrite that. See above. I told my students they can cite themselves on an exam. So if they've already proved something in a previous problem or, whatever, they can just say, as I showed in question 2 or as I proved here. Okay, so that's it. So that means x equals +4 is also in the interval of convergence. So now we know that the interval of convergence goes from -4 to 4, brackets on both endpoints. Okay, so you can see we do need to do a test for each of the endpoints. There isn't like a set outcome or a way to know just by looking. If I look at it and I know, it's because I did the test in my head, okay? It's not like there's any other clue. Okay, here's a fun one. We did this in class yesterday. We have the sum, n equals 1 to infinity, x minus 6 to the n over 2n factorial. Yes, we're going to start off doing ratio test as we have been. The factorial also is a dead giveaway. Okay, so here we go. Ratio test time. Do you have a favorite test? Because mine is the ratio test, so I'm really happy we get to do it so much in this unit. Limit, n goes to infinity, absolute value. X minus 6 to the n plus 1 over, watch out, 2 n plus 1 is in parentheses, please, factorial. Yeah, did we get it? Let me put my watch out eyeballs here. Watch out, don't mess that up. Times, I'm already going to multiply by the reciprocal, okay? 2n factorial over x minus 6 to the n. Good. Now, I want you to be careful here. 2 times n plus 1 factorial becomes 2n plus 2 factorial. The most common mistake I see is that students just make it 2n plus 1, but it should be 2n plus 2. That 2 needs to distribute. And that's going to dramatically affect the next few steps. So we have the limit as n goes to infinity, absolute value. This is x minus 6 to the n times x minus 6 over. Now what I'm going to do is start breaking down this factorial until I hit 2n so that it'll cancel with the other factorial. So I'm going to pluck off 2n plus 2. What's 1 less than that? 2n plus 1. What's 1 less than that? 2n. That's exactly the factorial I have on the other side. So I'm going to stop here, 2n factorial, times, and then here's the 2n factorial over x minus 6 to the n. How are we doing? Beautiful. So then cancel party, x minus 6 to the n cancels, 2n factorial cancels, and that's it. The cancel party has come to an end. So in the next step, I'm going to take out whatever doesn't involve n. In this case, it's going to be absolute value of x minus 6. Don't forget the absolute value. And then you have limit, n goes to infinity. What's left in the numerator? I know, nothing. Oh my goodness. Okay, so 1 over 2n plus 2 times 2n plus 1. Is that it? Yep. Okay, so now as n goes to infinity, look what's going on. I have a constant, so the numerator is not changing, and the denominator is going to infinity. It's getting very, very big. This is going to infinity. So where's this whole term going? That's right, it's going to 0. Huh, that's interesting. So now I have absolute value of x minus 6 times 0, which is just going to give me what? 0, yes. And remember, we just did the ratio test. So I want this limit to come out to be less than 1, but 0 is always less than 1, regardless of whatever I chose for x. I could have put any number I wanted here for x, even 2,047,000,000. And then times 0 would give me 0. So this is always true, which means all real numbers are part of the interval of convergence. So the way you write your answer is you say the interval of convergence is from negative infinity to infinity, and that also means the radius of convergence is infinite. This should be your favorite problem because you don't have to test the endpoints, right? So you're hoping your instructor puts one on the test like this, which, you know, I do, but I also throw in one where they have to test the endpoints. So that's it. There's no endpoints to test because it's infinite. Everybody's a go. Everybody works. This is such an agreeable little series. Don't we love it? Okay, perfect. So now let's go ahead, look at another example. That was short and easy. Number 4, we have the sum n equals 1 to infinity, negative 1 to the n, 4 to the n, over rad n times x to the n. If you want to pause the video, give it a try on your own. Feel free. Are you feeling confident? Do you feel like you got this? No? Okay, I'll keep going. I have no idea what you said, but I imagine some of you are over there shaking your heads like, no, not just yet, Professor V. Okay, so ratio test time. We have now the limit. N goes to infinity, absolute value. -1 to the n plus 1, 4 to the n plus 1, x to the n plus 1, over rad n plus 1, times, this is rad n, over -1 to the n, 4 to the n, x to the n. Okay, now let's break stuff up so we can have a cancel party. Also, I'm not even going to write the -1 to the n plus 1 or -1 to the n anymore. Because when I take the absolute value of each of those, it's going to become +1 to the n plus 1 and +1 to the n, which are just both 1. So we don't need them. We don't need them. Goodbye to them. So we have now limit, n goes to infinity, absolute value, 4 to the n times 4 to the first times x to the n, x to the first, over rad n plus 1 times rad n over 4 to the n, x to the n. I told my class yesterday I want theme music anytime there's a cancel party. So anyways, here we go. Imagine some theme music. 4 to the n cancels, x to the n cancels, and that's it, huh? Our cancel party has come to an end. I'm going to take out 4 and x from the limit. Make sure you keep the absolute value though. So absolute value 4x times the limit as n goes to infinity. And then I don't need the absolute value here. I just have rad n over rad n plus 1. Good. And then both numerator and denominator are going to infinity. So I'm just going to divide by highest power of n from the denominator. I'm going to divide by rad n. Divide by rad n. So this becomes, let's see, absolute value 4x times the limit, n goes to infinity. I'm just going to have 1 over, when I divide by rad n, this is going to basically become n underneath the radical. So I have rad 1 plus 1 over n. Yes? Yeah, I hope you're saying yes over there. Okay, so then this goes to 0. This whole limit's just 1. And then I'm left with absolute value of 4x. Beautiful. So I just did the ratio test. I need this limit to be less than 1 strictly. Not equal to. Don't you dare put that equals to. Oh, no, no. And then that's not my radius of convergence yet because notice x is not all by itself. So I'm going to need to multiply by 1/4 on both sides. And then now I have absolute value of x is less than 1/4. So that right there, my friends, that's my radius of convergence, 1/4. Good? Okay, now we have to figure out the interval of convergence. So x is between 1/4 and -1/4. Let's go ahead and test our endpoints. And the original series, let me rewrite it for you. It's the sum, n equals 1 to infinity, -1 to the n, 4 to the n, over rad n, x to the n. So let's plug in x equals -1/4 first. Let's see what we have. The sum, n equals 1 to infinity, -1 to the n, 4 to the n, -1/4 to the n, over rad n. Everybody in the numerator is being raised to the n, so I can group them in the same set of parentheses. So I can write this as the sum, n equals 1 to infinity, -1 times 4 times -1/4 to the n. Do you see that? Oh, good. Over rad n. And then what does all this give me? -1 times 4 times -1/4. It's +1, right? Oh, I don't need to write 1 to the n, but I will just for a hot second, because that's just 1. And what do we know about 1 over rad n? Yes, it's a p series. What's p equal to? Rad n, the exponent on n is 1/2, yes? Good, p is 1/2, and that's less than 1. So that means the series diverges. So that tells me x to the negative 1/4 is not in the interval of convergence. Nope, so sorry. What about positive 1/4? Shall we check? I mean, we have to. So x equals 1/4, let's check. So we're gonna have the sum, n equals 1 to infinity, negative 1 to the n, 4 to the n, 1/4 to the n, over rad n. Again, I can group everybody that's being raised to the n in the numerator. So n equals 1 to infinity, negative 1 times 4 times 1/4, all to the n, over rad n. Except this time, 4 and 1/4 cancel, but the negative 1 stays. Do you see how it's different? So this is the sum, n equals 1 to infinity, negative 1 to the n, over rad n. Oh, so, okay, now the alternating term stays, the negative 1 to the n. That means I'm going to do AST for this guy. So we're doing alternating series test. Bn is 1 over rad n. So first I need to show, is Bn decreasing? I don't need to take a derivative. I can just say Bn plus 1 is 1 over rad n plus 1, which is for sure less than 1 over rad n. So that's satisfied. And then condition 2, I want to look at the limit as n goes to infinity of Bn. 1 over rad n, yep, that goes to 0. So this tells me that the sum, n equals 1 to infinity, negative 1 to the n, over rad n converges by AST. So the endpoint that I was just checking 1/4, that does belong to the interval of convergence. So negative 1/4 did not, but positive 1/4 does. So we can write our interval of convergence as negative 1/4 with parentheses and then 1/4 with a bracket. So it's interesting because you notice every time we test endpoints, we do a test that we learned in a previous lesson at the beginning of the chapter. So this is a great way for an instructor who doesn't want to put a ton of questions on the exam to make sure you still know how to do AST or limit comparison test without having to put a problem just on AST on your exam. If they just put a problem like this, they're going to force you to do it. So be on the lookout. I don't know. If your instructor likes to make long exams with lots of questions, I don't know, but I don't like to put too many. I like to keep it around 10 or so. Once in a while I do less. And so questions like these allow me to check more concepts at once. Okay? If you're in my class, you know that. Moving on. Number 5, we did this in class yesterday. We have the sum, n equals 1 to infinity, x minus 9 to the n over 9 plus 8n. Okay, I think you can do this on your own. Why don't you pause the video? It's time to cut the cord. Run free. Okay, I hope you paused it and tried it. Let me flip through. Okay, I'm ready. Here we go. So we're going to do the ratio test. Here we have the limit. N goes to infinity. Absolute value. X minus n. 9 to the n plus 1 over 9 plus 8 times n plus 1 times 9 plus 8n over x minus 9 to the n. Good? Okay, let's break her up. Getting ready for that cancel party we love. Limit n goes to infinity. In the numerator here, now I'm going to write this as x minus 9 to the n, x minus 9 to the first. Distribute. So this is going to be 8n plus 8 plus 9 plus 17 times, let me just write it, 8n plus 9. And then here's x minus 9 to the n. Close or wrap. X minus 9 to the n cancels. That's it. The cancel party is over. No, you may not cancel these 8n's. Please don't think about such illegal maneuvers. The math police are going to come snatch you right up. They will. If you need to put parentheses to remember that they stay together, those are a little family. Don't break up the family. Don't be a homewrecker. Okay, do that. I'm going to take out absolute value x minus 9 from the limit. So let me do it then. If I'm saying I'm going to do it. Here we go. Absolute value x minus 9. Limit n goes to infinity. I don't need absolute value because now there's no more x's here. And then again, numerator and denominator are going to infinity. So I'm going to divide by n, highest power from the denominator. And then we have now absolute value x minus 9 times the limit as n goes to infinity of 8 plus 9 over n over 8 plus 17 over n. So 9 over n goes to 0, 17 over n goes to 0. All I have is 8 over 8. Well, that goes to 1. So now I'm just left with absolute value of x minus 9 times 1. And I require that to be strictly less than 1. That right there is my radius of convergence. Notice there's no coefficient on x. I don't need to multiply or divide by anything to get it by itself. This minus 9 means that the series is centered at 9. I'll show you in a second what I mean. But the radius of convergence in this case is 1. Now, since it's centered at 9, the endpoints are going to be a little different. So yeah, let's rewrite this. X minus 9 is less than 1, is greater than negative 1. To get x by itself, I add 9 to both parts of the inequality. So now I get x is between 8 and 10. So if you were to draw this on a real number line, you'll see how the radius of convergence is only 1. Oops. So here's 9, here's 8, and here's 10. Yes? So the radius of convergence is this amount right here, from the center to each of the endpoints, 1, 1. Later in math, when you introduce complex numbers, you'll have a full circle. That's why we say radius. But right now, we're only in the real numbers, so that's why it looks a little weird. But this is the radius here. This is the radius here, 1, 1. Okay, but it's centered at 9 because the x minus 9. That's all. So let's test our endpoints now. Here we go. Let's test the endpoints. Which one do you want to do first? You know, I can't hear you, so I'm just going to go with 8. X equals 8. So we have the sum, n equals 1 to infinity, 8 minus 9 to the n over 9 plus 8n. And this is going to simplify to the sum, n equals 1 to infinity, negative 1 to the n over 9 plus 8n. What test do you think we can use? It needs to be AST. It certainly does. So let's go ahead and use AST. What's Bn? 1 over 9 plus 8n. Good. So I have to check, is Bn decreasing? So Bn plus 1, that's 1 over 9 plus 8 times n plus 1. Oh yeah, that's for sure smaller than 1 over 9 plus 8n. So that's satisfied. And then the second thing I want to check is the limit as n goes to infinity of Bn 0. Well, yeah, denominator's going to infinity, 1 over infinity approaches 0. Perfect. So this means that the sum, n equals 1 to infinity, of negative 1 to the n over 9 plus 8n converges by AST, which means x equals 8 is part of the interval of convergence. Yay! Okay. Now let's check the other endpoint, x equals 10. So this time we're going to have the sum, n equals 1 to infinity, 10 minus 9 to the n over 9 plus 8n. And in the numerator, you're just going to get 1 to the n. And what did we say about that? 1 to the n is just 1, so you don't have to write it. 9 plus 8n. So look at this guy for a minute. It's reminding me of harmonic series. Isn't it reminding you of harmonic series? N equals 1 to infinity, 1 over n is harmonic, and it diverges. So usually you're going to use either direct comparison or limit comparison test when you have something very similar to a p-series. I can't use direct comparison because 1 over 9 plus 8n, it's actually a wee bit smaller than the harmonic series. Why do I say that? Because here I'm multiplying by 8 and adding 9, so this denominator is a little bit bigger, which means all of the terms are just a smidge smaller than the harmonic. And remember, if we do direct comparison, and I'm trying to show our series diverges, I need to show the inequality in the other direction. So this is not helpful. Not helpful for direct comparison. So what do? You don't cry. You just go, oh, I'm going to use limit comparison instead. So here we go. Let's use limit comparison test. And we take the limit, n goes to infinity. The terms of our series, 1 over 9 plus 8n, over the terms of the series I'm comparing it to, 1 over n. And then this is limit, n goes to infinity, n over 9 plus 8n. And then again, top and bottom are going to infinity, so I'm just going to divide by n, the highest power, in the bottom. And then I have limit, n goes to infinity, 1 over 9 over n plus 8. Well, this is just going to go to 0, and I'm left with 1/8. Do you remember what's important when we do limit comparison test? That this limit is finite and non-zero. And then limit comparison tells me my series does the same thing as the one I compared it to. So then I know the sum, n equals 1 to infinity, of 1 over 9 plus 8n also diverges, because I compared it to the divergent harmonic series, by limit comparison test. So the endpoint I was testing, 10, is not going to be in the interval of convergence. Nope. Sorry, 10. Okay, so let's write out then what the interval of convergence is going to be. It did include 8, but not 10. Okay. So I mentioned in the very beginning of the video that there were 3 possible outcomes, and here's the last one that I have not yet done for you. We have the sum, n equals 1 to infinity, of n factorial times 2x minus 1 to the n. So we're going to use the ratio test. I know we use the ratio test every single time. I told you on occasion you can use the root and it's easier, but if you don't, ratio will still work. Okay, so we have the limit as n goes to infinity, absolute value, n plus 1 factorial, 2x minus 1 to the n plus 1, over n factorial, 2x minus 1 to the n. So this is going to be the limit, n goes to infinity, absolute value. Let me break down n plus 1 factorial into n plus 1 n factorial. And then this is going to be 2x minus 1 to the n, 2x minus 1 to the first. And then we have n factorial, 2x minus 1 to the n. Good? Great. So let's cancel these out. 2x minus 1 to the n. n factorial is also gone. And I can take outside of this limit absolute value 2x minus 1. So let's do it. Absolute value 2x minus 1 times the limit, n goes to infinity of n plus 1. So if n is going to infinity, n plus 1 is going where? It's going to infinity. So this limit is, remember, this is just some constant. This limit is infinity, which is always greater than 1. So there's no way to force this to be less than 1. That means my radius of convergence is 0. I don't have a radius of convergence. And there's only one value of x that will make this series converge. You come back here and you isolate the term that has the variable x raised to the n. The only way this will converge is if what's inside those parentheses is a 0. So 2x minus 1 needs to be 0, which means x needs to be 1/2. So I don't have an interval of convergence. I have a lonely little point of convergence. So I'm just going to write the number 1/2 like that. So if you're looking at your number line, the only number that will make this series converge is 1/2, which is why we say the radius is 0. You can't move and have more values of x that make the series converge. This is the one and only value. And why is that the case? Because if x is 1/2, then every single term here gets multiplied by 0. So what ends up happening is your series looks like this. Okay, so n equals 1, you'd have 1 factorial times 0 if x is 1/2. Plus, then you'd have 2 factorial times 0 plus 3 factorial times 0 plus blah, blah, blah. And then you would just have a bunch of zeros added together. So of course it's going to converge. But how boring, right? Like you're just adding up a bunch of zeros. That's the only way this guy can converge. Well, yeah, because otherwise the terms are going to infinity. There's no way. So this is also nice because it's short. You hope the professor puts this on the exam too, right? Because then you have no endpoints to test. And that concludes the video. If you want a part 2, I can do it. If you want to see a couple examples where a root test works out nice, let me know down below. And I'll also link all the videos I have on sequences and series in the description should you need a review or you want just like a more spicy explanation on the topic, because that's my specialty. Subscribe if you haven't already. Give the video a thumbs up. Leave me a comment down below. Tell me which was your favorite. And also let me know where you're watching from. Most of my viewers are from the US. That's where I teach, but I also have so many from around the globe, and I love hearing where you guys are from. And if you need any help with Calc 1, 2, 3, I have full video lectures organized into playlists on my YouTube channel. I also have like algebra, trig review, pre-calc, you name it. And please follow me on Instagram, TikTok, Twitter, Math with Professor V. I love you all. I'll be back sooner than later. Bye.